Hello, I'm Rebecca Barnes. Welcome to the Science ESA vodcast. In this episode, we would take a closer look at Planck, a European Space Agency mission built to detect radiation from the microwave portion of the electromagnetic spectrum. This mission will help find answers to some of the most important questions in modern science. What is the universe made of? How did the universe begin? How did it evolve into the state we observe today? And what is in store for its future? The universe that we live in fact, space itself, is expanding. This is known from Hubble's law. If the universe is now expanding, this means that at some point in the past, all energy and matter must have been considerably hotter and more densely packed than it is today. This model of the beginning of our universe is known as the Big Bang. However, there are a number of things the Big Bang can't explain. For example, consider the very distant regions of space that are in opposite directions of the sky. They are so far apart that if you reverse time and the expansion of the universe, as described by the Big Bang model, you find that the light travel time between them exceeds the age of the universe. Something else is needed to explain this, and the theory that is widely accepted today describes a phenomena known as inflation.
Our universe is about 14 billion years old. In the beginning, a process called inflation caused the universe to expand exponentially. At the end of the short inflation period, a very hot, dense, and rapidly expanding plasma of fundamental particles was left behind. As this plasma expanded further, it cooled and generated the right conditions to form a soup of the building blocks of all matter, quarks, and electrons. After about 300,000 years, the first atoms formed, hydrogen and helium. Initially, these atoms were ionized. Photons were continually scattered by the free electrons and trapped inside the plasma. Further expansion cooled the plasma, enabling atoms to capture and bind electrons. At this time, the universe became transparent. The liberated photons were able to propagate freely in all directions. By now, the universe had cooled to around 3000 Kelvin, and so the energy of the first free photons was equivalent to infrared wavelengths. Since the universe became transparent, it has expanded more than 1,000 times, and the sky has cooled to just 2.7 Kelvin. The wavelength of these ancient photons has now stretched to microwaves. Despite their long journey towards us, these photons still preserve the physical information imprinted on them in the young, opaque universe. Today, they are detected as the cosmic microwave background, a relic from the Big Bang.
In 1965, Arno Penzias and Robert Wilson observed a continuous background radio signal that was spread over the entire sky. They had accidentally discovered the cosmic microwave background. Since then, two satellites, COBE, the Cosmic Background Explorer, and WMAP, the Wilkinson Microwave and Isotropy Probe, along with a number of balloon-borne experiments, have mapped the cosmic microwave background with increasing precision. After 40 years of study, it is now known that there are very tiny temperature variations right across the cosmic microwave background. These directly relate to the density of the plasma at the time light first propagated freely in the early universe. Denser areas eventually coalesced into the large-scale structures that we see today, stars and galaxies. What's more, these variations have been found to follow distinctive patterns that fit predictions made by cosmological theory and have been used to estimate the age, composition, and geometry of the universe. These experiments have also provided convincing evidence that our universe is dominated by mysterious dark energy and dark matter. There are still many unanswered questions. What caused the density variations in the early universe? Did the universe go through an inflation period? If so, what was its nature and what caused the rapid expansion? What is the nature of dark energy and dark matter? ESA's Planck mission will help to answer these questions about the nature of the early universe and much more. What makes Planck different to previous missions? Let's find out from the experts involved.
COBE and then WMAP have been setting the stage in a very clear way, in a very firm way. So in a sense, we know what to look for. Planck is the third generation satellite, which will have a much greater sensitivity and angular resolution in the sky to see the tiny details that will tell us about how the universe was and what its evolution has been in this 14 billion years.
There are some things which are very definite prediction that we will be able to do with Planck and which were not possible with previous satellites. And one of them is measuring something which is even more difficult than just detecting this fluctuation of the microwave background in intensity, seeing where the intensity is stronger than at other places, but looking at what physicists are calling the polarization. Polarized glasses, when sunglasses, the same type of principle where you observe basically how the light is vibrating, what direction is it vibrating into. And this extra information, there was very specific prediction of inflation for that. So if we find this signature, that will be not a proof, never completely sure, but a very strong indication that there was this period of inflation.
The Planck spacecraft carries a payload of two highly sensitive instruments, the Low Frequency Instrument, or LFI, and the High Frequency Instrument, or HFI. In total, 74 detectors covering 9 frequency channels will be used in this ESA mission to map the cosmic microwave background. The High Frequency Instrument is an array of 52 bolometric horn-shaped detectors that convert radiation into heat. The detectors work in 6 frequency channels centered between 100 and 857 gigahertz. This state-of-the-art instrument is like no other currently operating in space. The low-frequency instrument consists of 22 radio receivers that are tuned to 3 frequency channels between 30 and 70 gigahertz. They work like transistor radios, amplifying the signal collected by the telescope and converting it to a voltage.